Good afternoon, everybody. Welcome to the Ministry of Agriculture's webinar on interpreting soil tests. My name is Brittany Newmeyer, and I'm an intern extension agrologist with Saskatchewan Agriculture in Outlook, and I will be chairing this webinar today. We'll start the webinar today with a few housekeeping notes. If anyone has any questions during the presentation, you may type them in the question box in the bottom right-hand side of the control panel, and we will be sure to answer them at the end of the presentation. Keep in mind that when asking a question, it will be sent to only me and will remain anonymous. During the presentation, you will be muted so that there is no feedback that will interfere with the audio. The webinar will also be recorded, and a special link will be emailed out to you later today. Our guest speaker for today is Tom King with Northland Agronomy. Tom was born in High River, Alberta, and grew up in Okotoks, Alberta. He came to Saskatoon in 1991 to pursue a Bachelor's of Science in Agronomy. He then proceeded to complete a BCom degree. He came back in 2001 to do a Master's of Agriculture under Dr. Jeff Shano. He then stayed on to do a Master's in Soil Science. He examined the effects of manure application on soil carbon, light fraction carbon, and soil enzymes. He then decided to pursue a Ph.D. in soil science. His Ph.D. project studied nitrogen and phosphorus mobility and transport in soil that has received repeated applications of animal manure. He is currently wrapping up subsoiling and vertical tillage projects, as well as pulse seed row nitrogen projects, while learning the ropes of his new position at Northland Agronomy Western Ag. So with that, we will start whenever you're ready, Tom.
Thank you very much, Brittany. Yes, so those other projects, actually, I should have updated my bio a little better. Those were wrapped up here last spring, so they're long gone finished. So I've been with Northland Agronomy, which is a licensed business partner of Western Ag for Northwest Saskatchewan. And so thank you very much, Brittany and the other ladies, and to Corey Jacob for asking me to come today and present a little bit of information on interpreting soil test reports. So soil test reports are it's not rocket science, folks. It's pretty basic stuff, but there are some tricky things about them that sometimes can make them a little bit finicky to try and understand in that. So I'm going to kind of go through and try and cover as many things as I can here today about some of the different things that you'll see on a typical soil test report. So with that, when you're reading a soil test report, you need to first off take time to verify that the information that is contained within that report is all accurate. So things like the sample ID, the client ID or grower ID, when that sample was received and processed at the soils testing lab, things that identify the field, such as the legal land location, GPS coordinates, lat long, field name, things like that, need to always be checked to make sure that that's accurate, so that the information that's on the report pertains to that particular field that you're looking at or thinking about. Other things too is on a soil test report, the soil depth of the sample that's taken, is it a 0 to 15 centimeter, i.e. a 0 to 6 inch, 0 to 30, or 0 to 24 inch sample, etc. So it's always important to know the depth of that which that sample is taken, because nutrients levels and that can vary with the depth in the profile. Another thing that's very important to know too, and it's usually listed on the information when the sample is submitted to the lab, is the stubble type, i.e. the previous crop, and the crop that is to be grown in the upcoming year. Now, if there are any doubts about the analysis results, and sometimes this does crop up, there are some mystery numbers or numbers that are just way out of sequence. Sometimes if you're doing soil sampling late in the fall and you're measuring phosphorus, sometimes you can get some very abnormally high phos levels. And that can be due sometimes to situations where freeze thaw occurs. It thaws, and then there's another freeze effect again. And so more of the phos can be released from the crop stubble of the previous crop, and that can abnormally inflate the the phosphorus numbers that are presented in the report. And so it may necessitate another follow-up trip to the field and another resampling again to try and get that under control and see if the numbers are correct or not. And the last thing you should always ask yourself when you're looking at these soil test reports are, do the numbers for each element make sense? Okay, are those numbers, do you think they're correct, or are they just way out of whack? If they're way out of whack, then go back, resample again, and do another test and see if you can get the correct information to that, or confirm that the information you're looking at on the particular report is the correct information. So we've all seen soil test reports before. They all kind of sort of come with the same basic information. They'll have information about your macronutrients, nitrogen, phosphorus, potassium, sulfur, your what I call the mini macros, calcium, magnesium, your micronutrients, copper, iron, zinc, molybdenum, manganese, etc. Things like soil quality things like soil pH, cation exchange capacity, soil salinity, or as measured by electrical conductivity, things of that sort. Soil texture, some labs will break it down, like on this particular report I'm looking at here, we'll break it down into the individual sand, silt, and clay portions, the mineral portions of the soil. Other labs will just simply list it as being a loam or a silty clay loam or a sandy loam or whatever. Other reports from labs can always vary a little bit. This particular lab report here, I'd like to give a shout out to my good friend Chris Ban at Aegeus Agricultural Consulting down in Swift Current for sending me this one here last fall. So great looking little report there. This particular report, he's got it broken down in there. He sampled at 3 different depths here when he was looking at his soil for this particular field. Another type of report, soil health test report, and that again, some little bit more information that can be contained within, such as, and I'm going to go into things like pH, buffer pH. What the heck is the difference between pH and buffer pH? I'll go through that here in a couple of minutes. Things like base saturation, things of that sort. So with that, first thing I want to bring out to people is in the analysis report, pay attention to the units. Now, sometimes, excuse me, a report will list the elements or the nutrients in parts per million. Sometimes they'll list it in kilograms per hectare, or sometimes it's presented in pounds per acre. So the first thing I'll do is I'll go through what's the difference between kilograms per hectare versus pounds per acre. Just want to make note that 1 hectare is equal to 2.47 acres. 1 kilogram is equal to 2.2 pounds. So when you want to convert kilograms per hectare to pounds per acre, so for example, if you had a report that listed a nutrient at being 52 kilograms per hectare, you multiply by 0.89 to convert that to the pounds per acre. Conversely, if you want to convert from pounds per acre to kilograms per hectare, you take that number. So if you've got 37 pounds per acre of a nutrient, you multiply that by 1.12 to get 41 kilograms per hectare and get your kilograms per acre, or excuse me, per hectare. Parts per million. I've had some people insist that ppm is actually pounds per million. That is very incorrect. It's parts per million. 1 part per million is equal to 1 microgram per gram, which is equal to 0.0001%, or 1% is equal to 10,000 micrograms per gram. Being a scientist, I usually work in SI units, so I like to work with kilograms per hectare or micrograms per gram. Now, some labs will multiply parts per million values by a factor of 2 to generate the kilograms per hectare or pounds per acre concentration of nutrients in a 0 to 6 inch or 0 to 15 centimeter depth of soil. Now, where does that 2 factor come from? Well, that 2 factor is based on the standard soil bulk density of about 1.4 grams per cubic centimeter. And in an acre, 1 acre of land, which is 43,560 square feet, to a 6-inch depth, there are roughly 2 million pounds of soil in an acre furrow slice. It's actually about 2.2, but we slim that down a bit and just use the 2 factor. For a little bit more information on the acre furrow slice explanation, I would refer you to Les Henry's excellent book, Henry's Handbook of Soil and Water, in which he goes through a very good full explanation of the acre furrow slice, or conversely, you could call it the hectare furrow slice. Now, multiplying the parts per million, or the micrograms per gram, in a 0 to 15 centimeter layer will generate the kilograms per hectare, or pounds per acre of nutrient. So that's kind of a brief explanation on units. So always pay attention to the units that are on a report. Every lab reports them a little differently in that, so it's always essential to make sure that you're comparing apples to apples or oranges to oranges. So let's go into the first couple of things here. Let's go into the soil pH. So the soil pH scale, so when pure water dissociates into its components, hydronium, which is H+, and hydroxide, OH negative, the ion product is broken down, and we get a factor, or a Kw factor, of 10 to the minus 14. So what that translates to is, when converted, excuse me, folks, too much coffee this morning. When converted to whole numbers, the pH scale is therefore from a scale of 0 to 14. Make note, there are no units associated with pH, no pounds per acre, no millisiemens per centimeter, or anything like that. So if you've got a pH that's 0, that's very acidic. A pH that's 7 is neutral, and a pH that's 14 is extremely basic. In soil solution, a pH value that's really lower than 4, which is or more acidic, or more basic, or greater than 9, is actually relatively uncommon. Soil samples that are sent to the lab, pH is usually measured using one of two ways, either using a 2-to-1 soil to water mixture, so 2 parts soil to 1 part water, or they will do what they call a saturated paste. And that's where they add a little bit of water to the soil sample, they mix it up in a pile, and they'll take and dip in a spatula, and when they hold the spatula at about a 45-degree angle, the soil sample and water will just kind of slowly slide off that spatula. That's when they know they've got the right consistency of water to soil. Now that's soil pH. Now, sometimes on a solids report, you can also see something called buffer pH. What the heck is buffer pH? Well, some US and Eastern Canadian soil testing labs will measure this, and they will report that on the report. Now, there is a bit of confusion between the measured soil sample pH and the buffer pH. What the buffer pH does is that qualifies acidic soil pH by estimating how much liming amendment is needed to raise the soil pH to a preferable level. Now, because here in Saskatchewan we have very highly calcareous soils, our soils are pretty much mostly alkaline soils, liming is not a typical farming operation done here, whereas it is done to a great extent in the United States and some places like Eastern Canada. So the soil buffer index measures how much reserve acidity is present, or i.e. the remaining hydronium ions contained within the soil organic matter and the mineral components. So the buffer index is determined by adding a chemical solution of a known pH, i.e. the buffer. And that's added to the soil solution. They do that after the soil's pH has actually been determined. They'll add this buffer. So then the amount of change in the sample pH measures the amount of reserve acidity, or the buffering capacity. So the buffer index can then be calculated, and this can be used to determine a liming amendment rate that's needed to raise a soil pH to the desired pH level. So the buffer index depends on the amount and type of clay. So things like 2-to-1, 1-to-1 clays, things like montmorillonite, kaolinite, and the level of organic matter that is in a soil. Cation exchange capacity can also influence the soil organic matter and clay on a soil buffering capacity. So that is the difference between just regular normal pH, soil pH, and the buffer pH. They're adding a chemical of known pH to the solution to raise that pH up, and then it determines the amount of reserve acidity or the buffering capacity, and then they can calculate the amount of lime that's going to be needed to raise the pH up in a soil. Not something that's commonly done up here in Saskatchewan. Just before we move off pH, just want to make folks aware that different nutrients can behave differently in different pH soils. And pay attention to phosphorus, because phosphorus is a different breed of cat compared to nitrogen or sulfur. Nitrogen or sulfur is typically available at a fairly wide range of pH, whereas phos is really only available kind of between that pH of 6.5 or 7.5. Once we get into higher pH soils, phosphorus levels can be more tied up in the calcium magnesium complex and become unavailable. You drop down below 6, and phos can then be tied up with that iron and aluminum, which dominates in lower pH soils. So just be aware of that. Soil salinity. A soil is considered saline if it contains sufficient soluble salts which reduce plant growth, i.e. those salts prevent plant roots from taking up water. The cells in that are blocked from being able, by the salts, from being able to take up soil. So the most common soluble salts here are sulfates and chlorides of calcium, magnesium, and sodium. Salinity measured by electrical conductivity. So the salts will convey an electrical charge, and the probe will be inserted into that solution. Just as can be the same solution that's what's done for a pH, that 2-to-1 soil water mixture or the paste. And insert the probe, and then the electrical conductivity can be measured. So the ability of that soil solution to conduct an electrical current is in direct proportion to the concentration of the soluble salts. So that conductivity meter measures the amount of current that's passing through the soil solution, and then this can be related to the concentration of soluble salts in the solution, i.e. the salinity. Units of measurement, generally millisiemens per centimeter or decisiemens per meter. You can do a conversion from one to the other, you'll get the same number. Essentially, folks, if you've got a soil sample and the salinity is at 4 millisiemens per centimeter or greater, you've got a saline soil. And I would argue too that if you've got a measurement that's at least 2, you've got a soil that's well on its way to becoming a very bad saline soil. So again, as I mentioned earlier, saturated soil paste or a 2-to-1 or 1-to-1 water suspension. The 1-to-1 method is probably faster to carry out, but more difficult to interpret because the values will change with changes in soil texture, moving from a coarse textured soil to a medium to a heavier clay textured soil. Just a chart here that I found and put on. Like I said, if you've got a soil that's at least 4 decisiemens per meter or millisiemens per centimeter or greater, you've got a soil that is actually very, very, very saline. If you've got something that's less than 1, it's very, very non-saline. So different degrees of salinity. Moving on, sometimes on a soil test report, you'll see something called the SAR, or the sodium absorption ratio. Now, the SAR is a less common analysis, but it describes the proportion of exchangeable sodium ions to exchangeable calcium and magnesium ions. So the SAR calculation, so it's a very simple calculation. So they'll measure the amount of sodium, calcium, magnesium in a soil sample. They'll plug that into a calculation there, and they'll come up with a number. Now, soils with a SAR that's greater than 13 are sodic, also known commonly as alkali, not alkaline, but alkali soils. Soils with a higher sodium causes the soil particles to repel or flocculate or disperse, especially bad in clay. This causes poor soil structure. It limits the pore space, limits water infiltration, limits root exploration, and creates more surface crusting. So as I like to say, if your plant roots can't grow down, your plants then can't grow up. Another test that you might see on a soil test report, exchangeable sodium percentage, ESP, not extrasensory perception, but exchangeable sodium percentage. Now, it's an analysis which is used to describe the sodium status of the soil, just sort of like with SAR. It's probably a little bit better way to describe it. It describes the degree to which the exchange complex is saturated with sodium ions. So in the formula for that, exchangeable sodium divided by the cation exchange capacity times 100 gives you your ESP. So characterizing that exchangeable sodium is very useful in identifying solonetzic soils. What is a solonetzic soil? Well, that is a soil that has a B horizon, which is enriched with sodium and clay, the old BNT, that hard pan layer. You dig down in a pit and you get past the A horizon or your topsoil, and you hit that kind of sort of a columnar type structure there, encrusted with more sodium ions and that. Very hard to dig through, very hard for plant roots to get through. The sodium hazard of the soil then determined by factoring in the electrical conductivity and the sodium absorption ratio. So we can classify these soils depending on the following. If they're a sodic soil, they've got an ESP greater than 15, a SAR greater than 13 to 15, high pH soils greater than 8.5, and electrical conductivity that's less than 4. They're not saline, but they're sodic. They've got a very high sodium ratio. Now, a saline sodic soil has an ESP greater than 15, a SAR greater than 13 to 15, but a pH less than 8.5, but an EC greater than 4. And then a pure saline soil, an ESP less than 15, a SAR less than 13, 15. So sodium ions are not present, but your pH is less than 8.5, and your electrical conductivity is greater than 4.0 and that. So sometimes you can have that saline sodic soil, and we'll get producers asking, they want to go through with a deep ripper and rip that open. Sometimes that sodic layer can be holding back saline salts. So sometimes it's better just to leave that soil alone, not deep rip it, and keep those salts down below, because if you do rip it, you're going to allow those salts to migrate upwards to the soil surface, and now you've compounded a problem that you already have with another problem. So that is always an important thing to note and be cognizant of. Cation exchange capacity. So ion exchange in the soil, it's important for influencing crop nutrition. So CEC is an estimate of the soil to absorb cations. So what are cations? Calcium, magnesium, potassium, sodium, hydronium, aluminum, and release positively charged cations. So the units of measurement, and you'll see this on a report, sometimes it's reported as centimoles per kilogram or milliequivalents per 100 grams of soil. It could be one or the other. It's influenced by the soil texture, whether it's a coarse, medium, or heavy textured soil, and the amount of organic matter. So high to low CECs generally flow from a clay textured soil or a heavy soil. They'll have a higher cation exchange because there are more exchange sites on the clay minerals. Falls down to silt and then sand. Sand, less clay in a sandy soil, loamy sand, sandy loam, and that less exchange sites that you'll see there. Less organic matter, less clay, less exchange sites. The type of clay can also influence the cation exchange capacity. So whether it's like a 2-to-1 clay, something like montmorillonite, or if it's a 1-to-1 clay like kaolinite. I'm not going to go into clay mineralogy and clay chemistry because that's a whole topic unto itself, but just to be aware of that as well too. Generally, most of the time, they do not report on a soil test report, whether it's a 2-to-1 or a 1-to-1 clay or whatever. But just be cognizant of the fact that the type of clay will influence your cation exchange capacity. Most of the time, the direct measurement of cation exchange, it's time consuming, usually not part of a basic analysis package. And again, clay and organic matter, the direct components of the soil that influence cation exchange capacity. Soils with a high CEC, generally 10 to 50 milliequivalents per 100 grams. You'll see that with a higher clay content, higher soil organic matter content. They'll have higher water holding capacity. They'll resist changes to soil pH. and they're less susceptible to leaching. Soils with a lower CEC, generally in that 1 to 10 milliequivalents per 100 grams of soil, they're more coarse textured sandy soils that are low in soil organic matter, low clay content, they've got a lower water holding capacity, and they've got a higher ability to leach nutrients. Now here's one that I see on soil test reports, and people get really worked up by this, and it's called base saturation, or BS, base saturation. Now, what base saturation is, it's a measure of the total soil cation exchange capacity occupied by cations, calcium, magnesium, potassium, etc. And it's expressed in a percent. So while there's no real ideal percent base saturation, these values are sometimes used to make recommendations for calcium, magnesium, and potassium fertilization. Really, what base saturation is just another way to express the soil pH. And really and truly, soil pH is one of the items that is usually done on a soil test report. You get the actual soil pH, and that, so it's a better measure of that describes your soil pH. It's base saturation, not a useful concept in alkaline soils, which we have dominating here in Saskatchewan, where it can meet or even exceed 100%. Now, base saturation is based on research that was conducted in New Jersey back in the 1940s. And it was believed that fields needed certain base saturation levels to ensure proper nutrient uptake. Now, as they did more research this in the 50s and 60s and that, really, they found that the original testing of that and the design of that was flawed. And really, it revealed that base saturation ranges had very little effect in determining nutrient levels in agricultural soils. And one of the issues with base saturation is that it fails to take into account excessively high levels of cations. And really, it should only be used really as an indicator of soil health and not as an indicator of what you need for nutrients. So that's all I'll say about base saturation. I see base saturation on reports and it kind of irks me a bit, so I won't go into any more than that. Turning now to soil organic matter. So soil organic matter, of course, we know it's defined as dead and dying plant, animal, or microbial tissue, although plants supply most of the carbonaceous material that ultimately produces the majority of our soil organic material. However, we do have things like microbial tissues, bacteria, fungi, actinomycetes, and that also make up soil organic material. In Western Canada, the organic matter content of most surface soils ranges from about 1 to 10% on a weight-by-weight basis. If your organic matter exceeds 17%, according to the Canadian System of Soil Classification, then you have a truly organic soil or peat soil. And in fact, if you go out east of Tisdale into the kind of the Hudson's Bay area and that, you'll find some definitely high organic matter peat soils up in that region. So what it does is the soil organic matter, it serves as a fluctuating nutrient and water source or bank, which can tie up and or release nutrients and water over a period of time. So together with the cation exchange capacity, the clay content of your soil, soil organic matter has a large impact on nutrient mineralization and immobilization processes. I won't go into mineralization and immobilization today because, again, that's another whole topic for another day on by itself. Just a chart here I included here, organic matter content of different soil associations here in Saskatchewan. If you've got a Regina heavy clay, you're down there in that brown or the medium brown zone. You can have anywhere from 4 to 5% organic matter in that uncultivated surface. After about 75, 80 years of cropping, it could be reduced now to about 3%. Up in Melfort, silty clay loam texture class, you're in the gray-black soil zone, you can have organic matters that can go anywhere from 12 to 15, even up into the organic matter range past 17%. Shellbrook area here, northwest of Saskatoon, more of a fine sandy loam, so a little bit coarser textured soil, or the gray-black. You can have the organic matters that are about 6 to 7%. Should point out too, organic matter Organic carbon makes up roughly 50 to 55%, usually typically on average about 52% of the organic matter that is in a soil sample here in Saskatchewan. So most common laboratory procedures for measuring soil organic matter is what they call a loss on ignition. So that's where the sample is heated or incinerated, and after they've taken it out of the oven, only the ash remains, and the soil organic matter content is the difference in the weight that was measured before and after heating. Some more precise measurements are used to determine the soil organic carbon, or the OC content, by measuring differences between total carbon and non-organic carbon. What's non-organic carbon? Things like carbonates in a soil sample and that. So again, incineration is used and that to measure the differences between total carbon and total non-organic carbon, and that so it can be incinerated at different temperatures. And organic carbon can then be used to also calculate a C to N ratio in a soil sample. And oftentimes, not always, but your C to N ratios can also be included on a soil sample test report. I'll come back to that in just a sec, but what I'll do here is I'll move on to plant available nitrogen now. So I'll start to get into some of the macro elements. So the big one, nitrogen. Sometimes on a report, you'll see just nitrate nitrogen reported. Sometimes you'll see ammonium nitrogen reported as well. Now, ammonium nitrogen is the cation form of nitrogen. Plants do take up some N in the form of ammonium, but oftentimes the ammonium is converted to nitrite, which is NO2 negative, and then finally to nitrate by our good friends, the nitrosomonas and nitrobacter bacteria guys. So most of the time, most of the N is in a nitrate form. It doesn't remain in that ammonium N form for very long. So oftentimes you'll see the ammonium N numbers on there will be very low compared to the nitrate N numbers. So be aware of that. So again, it depends on the concentrations of ammonium and nitrate, the biological activity, things like temperature and moisture conditions in a soil sample or in a field will change in that and fluctuate in that. So that will depend on how much things like mineralization and immobilization will occur with a sample. Just point out too that, of course, the plants have a large requirement for N, and really only carbon, hydrogen, and oxygen, things that we really can't influence that much, are in greater concentration in plant tissue. And again, plant roots take up mostly N in the form of nitrate, but they will also take up N in the form of ammonium. What is N important for? Well, things like plant proteins, amino acid development. Nitrate, beware, nitrate is a mobile element in soil, and it can be lost and often is through leaching. So coarser textured soils and that, you get a rainfall, that more of that N can be moved down further down in the profile. Usually sandy, coarse textured, well-drained soils will have lower N supply. If that soil N in the top 0 to 15 centimeters or top 0 to 6 inches is low, additional inputs of N may be required to supply enough N to the growing plants in the early part of the growing season. So again, knowing the soil texture on your samples and that is definitely an important thing to know, especially when you're making your N fertilizer recommendations. Again, some labs will report nitrate and ammonium. Some of them will just simply report as nitrate. Some labs will also sometimes report what they call the total N. The total N is the combination or the addition of inorganic nitrogen and organic nitrogen. Organic nitrogen is plant unavailable. Now, sometimes some of that N can be mineralized over a growing season. How much so? It varies field by field, region by region. It's a hard thing to pin down. But really, the total N is kind of sort of, okay, it's an indicator of how much total N do we have in the field, but it's not a good indicator of how much actual inorganic nitrogen is available for plant take-up. Oftentimes, your nitrate is reported as pounds per acre or the kilograms per hectare. It can even be reported as parts per million. So again, folks, when you're looking at a soil test report, make sure you're paying close attention to the units or the reporting units by the lab. Every lab is different. Soil N doubles, generally if you got anything under 30 pounds of N, you've got a low N supply. anything that's between 60 to 100 pounds of N is probably a medium level of N, and high N is usually anything that's over 100 or 110 pounds per acre of N that's available. Just a table that I included here, crop nitrogen requirements. It's a bit outdated now because we're certainly growing more wheat that's above 40 bushels per acre, and certainly canola that's above 35 bushels per acre, but just kind of a proportional breakdown for wheat, how much N is taken up in the seed and the straw. For wheat, usually 55, 65 pounds of N in the seed. Straw is around 20 to 30 pounds. Canola in the seed, usually 60 to 75 pounds of N, and straw in that 30 to 40 pound range of N. And certainly that's going to be higher now because we are seeing canola yields that are 50, 60, 70 pounds per acre. Wheat, 70, 80, 90 bushels per acre, excuse me. So now those numbers there's even going to be even more. So crop nitrogen requirements for those crops now today are much greater than they were even 5 to 10 years ago. Just moving back to carbon, so carbon to nitrogen ratios. So any time you have a carbon to nitrogen ratio that's 20 to 1, so 20 parts carbon to 1 part of N, you will have immobilization going on. Anything that's under a CDN ratio of 20 to 1, you can have mineralization occurring. So be aware of that. And sometimes you'll see that carbon to nitrogen ratio reported on a soil test report. Moving now to phosphorus. Okay, phosphorus, important for seed germination, root development. Phosphorus helps adsorption, adsorption. Now, I'll go into a bit here. Sometimes you'll see on a soil test report, you'll see Malick, Bray, Olson, or you might see Na bicarb. Olson is the bicarb method or the sodium bicarbonated method. Sometimes you might even have a lab that'll do the modified Kelowna test. Modified Kelowna was developed here at the U of S back in the 1990s by Dr. Tian and Dr. Shano. Olson bicarb or modified Kelowna test should be done on soils that have a neutral to high pH, i.e. a pH that's greater than 6.3. I'll get into Bray and Malick here in the next slide. Just remember too that phos is usually not mobile in the soil, so it should be tested. Samples should be taken from that 0 to 6 inch or 0 to 15 centimeter depth. On soil test reports, it's usually expressed as an oxide, which is P2O5. Now, P2O5 does not exist. It's an oxide. But because the fertilizer industry expresses phosphorus and potassium as an oxide, P2O5 or K2O, then soil test reports will usually present that phos information as an oxide to match how the P is presented for fertilizer. Generally, it can be reported as parts per million or micrograms per gram, parts or pounds per acre. Again, pay attention to the units. Bicarb levels, anything that's probably under 3 micrograms per gram is low. Anything that's over 12 to 15 micrograms per gram of phos is a high level of phos. Now, I see this on soil test reports. I see a lot of times, and you'll see this in Eastern Canadian soil test labs, American soil test labs. They do the Bray, what they call the Bray 1, or the Malick test. Those soil tests should be done on lower pH or more acidic soils. So, i.e. a soil that's under 6.2. Again, we've been through this. Soil P is not mobile. For a Bray, if you've got a soil P that's under 5 micrograms per gram, that's a low P. If you've got anything that's over 20 micrograms per gram, that's a high soil P. So Bray and Malick, I like to see that done on an acid soil. So if it's a lab from Ontario or Quebec where they have more acid type soils, then that's fine. But here in Western Canada, in Saskatchewan, we have relatively high pH soils. You got to travel a long ways to find a real low pH soil. And really that's where the Olson bicarb or even the modified Kelowna test should be done on your soil samples for phosphorus. Potassium, important for overall growth, standability of the crop, to resist lodging, disease resistance, things like that sort. K is not mobile in the soil. Usually it's an ammonium acetate exchangeable extraction procedure that's done in the lab. Again, it's presented, that information is presented on the soil test report as an oxide, K2O, that doesn't exist, but it matches how the K in that fertilizer is reported. If you've got anything under 150 micrograms per gram of K, that's a low K level. If you've got anything over 250 micrograms, you're moving into higher soil levels of potassium. Moving to sulfur. Okay, sulfur helps increase the protein levels in plants, aids in formation of nodules and legume crops. Sometimes if you've got a deficient soil that's deficiently low in sulfur, that can result in inhibiting the amount of nitrogen that's taken up by a plant. And I've seen this in things like canola up in the Melford area and that, where you've got soils that used to be low in sulfur. The last number of years, though, producers have been adding more sulfur to the soil, so chances are being able to see a soil that's low in sulfur now is relatively uncommon. Sulfur or sulfate sulfur, it's mobile in soil. You may have to sample down to a 0 to 12 or 0 to 24 centimeter depth to find all of that sulfur. So in sandy, coarse textured, well-drained soils usually are low in sulfur. Crops such as canola and oats, they usually have very high sulfur requirements. And if you've got anything that's less than 25 pounds of sulfur, you've got a low sulfur level. Anything that's over 40 or 50 pounds sulfur in an acre, that's usually a high sulfate sulfur in that soil sample. Calcium, what I call the one of the macro mini samples. It's taken up by plants similar amounts to phosphorus. It aids in plant response to environmental and disease stresses, aids in plant absorption of other nutrients. Calcium is not mobile in the soil, so it should be tested at that 0 to 15 centimeter soil depth, usually reported as parts per million or micrograms per gram. Anything that's lower than 500 micrograms per gram is a low level of calcium. The other macro mini, magnesium, important for plant photosynthesis, also helps pulse crops fix nitrogen for nodule production. It's usually less available to plants in that lower than 5.5 range and in sandy, coarse textured soils. Magnesium is not mobile in the soil, so it should be tested in that 0 to 15 or centimeter or 0 to 6 inch depth. It's usually reported in a parts per million or micrograms per gram. If you've got a low magnesium level, it's usually under 50 micrograms per gram. High is usually anywhere over 100 micrograms per gram of magnesium. Now I'm going to turn to some of the micronutrients. So boron. Boron is important for reducing nutrient disorders in plants, and note that boron is actually toxic to things like peas and some of your dry beans. In the lab, it's usually done with a EDTA, or what they call an ethylene diamine tetraacetic acid extraction. There are usually two common boron species in the soil, what they call boric acid and borate anion. Those are the two common ones, forms that are found in soil. It's usually more available to plants in that 5 to 7 pH range. So if you go past the pH of 7, it's usually less available. The pH it's getting more tied up. It's a very mobile element in soil. So in sandy, coarse textured, low organic matter soils, well-drained soils can often be found with maybe lower levels of boron. Again, reported as parts per million. If you've got anything under a 0.5 microgram per gram level of boron, that's a low level. Anything over 1.0 micrograms per gram of boron, that's a higher level of boron. Turning to copper. Higher levels of phosphorus, zinc, and iron will inhibit the ability of a crop to take up copper. Usually extraction is done with DTPA, so diethylene triamine pentaacetic acid in the lab. Cereal crops are especially sensitive to low levels of copper. So things like wheat, barley, rye, they're very sensitive to lower levels of copper. And it may be when if you've come back with a sample, not oftentimes do you find that the whole field is deficient in soil, but on more sandy or coarse textured parts, hilltops, lower organic matter areas of a field can often be found to be lower in copper. It's not a mobile element, so it should be tested in that 0 to 6 inch or 0 to 15 centimeter depth. Reported as parts per million. If you've got a low copper rating, you've got under 0.25 micrograms per gram. Anything over 0.5 micrograms per gram, that's a high copper rating. Iron, important for end fixing and legumes. Generally not an element that's really found to be really deficient in Saskatchewan soils. It's really got a low availability of plants. It's not mobile. And again, soil iron supplies are usually pretty adequate. Anything under 2.5 micrograms per gram, it's a low level. Anything over, that should be, it's a stake there, that should be 5 micrograms, not 0.5, but 5 micrograms is a high level of iron. Manganese, important for seed germination, reducing the time to harvest as it enhances the phosphorus and calcium availability to a crop. It's not a mobile element, so it should be tested in the 0 to 15, 0 to 6 inch soil depth. Soils with a higher pH and higher organic matter can be found to be lower in manganese. Again, reported as parts per million. Anything under 0.5 micrograms per gram in a sample is a low test level for manganese. Anything over 1.0 is a high micrograms per gram is a high level of manganese. Zinc, important for root development and the rates of seed maturity and for stalk strength in plants. Extracted with DTPA, it's not a mobile element in the soil, so it should be tested in that 0 to 15 centimeter or 0 to 6 inch range. It can be tied up and plant unavailable where you've got high soil test levels of phosphorus. So phosphorus can actually act to tie that zinc up. So be aware of that. It's usually reported in that parts per million or micrograms per gram. Anything under 0.25 micrograms per gram is a low zinc rating. Anything over 1.0 micrograms per gram is a high level of zinc. So moving past the macro and the micro elements. So just when a lab is making a suggested fertilizer recommendation guidelines here, usually those suggested fertilization rates that they're giving you, they're based on actual university research. So research has been carried out at the University of Saskatchewan, University of Manitoba, places like that. They've done small plot studies in that, and they've come up with recommendations in that, which are used to update and produce things like Provincial Agricultural Department guidelines. Things like the provincial guidelines to safe rates of fertilizer application with different crops and that. It's also based on literature that has been published. It's peer-reviewed literature undertaken when the researcher publishes that by other researchers and that. So it's usually generally very good, very factual information. So in order to use a soil test report properly, the agronomist has to understand all that information that he or she is being given, what the relationships of the various reported components mean, and you got to be able to make some educated and informed decisions as to things like the 4 R's, the source, rate, time, and placement of your applied nutrients to achieve your cropping goals. So things like properly managed fertility programs as best management programs or BMPs need to be adhered to as well too in cropping systems. So that provides the best economic, social, and environmental benefits. We don't want to apply nutrients to the point where we're not going to see an economic benefit from that, but we're going to see an environmentally detrimental adversity occurring, such as applying too much N in a coarse textured soil, the plant being able to only take up so much to produce a certain yield level of a crop, and then the rest of that N, if it's a coarse textured soil, and that can be washed down in the profile, ends up contaminating things like groundwater and wells and things like that. So we certainly don't want to see that. So we want to see growers and their advisors and that adhere to the 4 R's and certainly adhere to the best management programs. Now, this is a question that we've gotten, and I know Dr. Chino gets this question all the time. So I sent my sample to 3 different soil labs, and they came back with 3 different recommendations for nutrient application. So what is up with that? Well, it depends on where that particular lab is located. So if samples are being sent down into the Midwestern US, down into Nebraska, for example, or samples are being sent into Eastern Canada, for example, and that you can get different recommendations based on different philosophies from the particular region that that lab is located in. So one set of recommendations for fertilizer application or nutrient application can be based on the philosophy that nutrients should only be applied in an amount sufficient that will get you the best economic yield increase that can be expected. And that's it, no more. Another fertilizer guideline philosophy that could be presented on a soil test report could be based on just simply maintaining a soil supply of nutrient equal to that the plant is expected to remove during the growth and harvest, and no more. So the recommendation will be basically apply the amount of nutrient only equal to this particular plant, the expected plant growth growth and yield that's going to be removed, and you apply only to meet that. The other one, the first one, is that you apply nutrients to the point where you keep getting an economic yield increase. Yet another philosophy could entail nutrient building over time. And we get this question all the time. We get to growers where the fertilizer dealer has some extra potassium, for example, and they're going to get a deal on if they take it. So they may want to decide, well, I've got some potassium deficient fields. I'd like to build up my fat potassium, even though my plant can't use it, all of it this year and that, but for future use in that, I'm going to apply a little bit extra. And certainly something like a non-mobile nutrient like potassium, that can be done. So again, that is another rate recommendation philosophy that can be presented in a soil test report. Soil sampling, just a little bit here. So again, nutrient amounts can certainly vary with soil depth. So, and you have to consider mobile nutrients versus non-mobile nutrients. Things like nitrate, sulfate, sulfur, even sometimes phosphorus, which is considered to be a non-mobile nutrient. Sometimes, if the exchange sites in that are full, some phosphorus will move a little bit down in the profile. So be aware of that. So again, your type of soil sampling, you've got to determine the objectives that have to be met, what type of crop you're going to be growing in that, the nutrients that you're trying to determine in that. So that all has to be considered when you're doing your soil sampling and that, so that you don't end up with what they call a GIGO situation, garbage in, garbage out, where you've taken an improper sample and now it's going to end up giving you erroneous information. So when attempting to determine the amount of nutrients for an upcoming sample, sample to a depth where the majority of the plant root activity, i.e. that 0 to 6 inches or 0 to 12-inch depth, is going to be located. I've seen soil test reports where people go down to 2 feet. That's fine, but again, it's probably that upper soil depth, that 0 to 6 inch, which is the most active layer in the soil profile where most of the nutrients are concentrated. So when the nutrient is applied at a certain depth, it's also essential to measure the amount of nutrient that remains at that depth too. So, and I'll go into this in the next slide here, be cognizant of your seeding and fertilization equipment that your client or your grower uses when they're applying their seed and their fertilizer. So again, yes, so make sure that the method of nutrient application is known. Does your producer seed row place only? Does he do a combination of seed row place and side banded? Or do they use a mid-row band? You need to have this information. So again, you learn this through consultations with your grower and that to know what kind of equipment they have in that. And it's essential to have this information when you're soil sampling that. And when you're making fertilizer recommendations. Because sometimes the soil test report may call for a huge amount of N to be put on to grow a certain level of crop, but your producer has equipment that just is simply not able to push that amount of product through their unit without doing a separate banding operation and that. And they may be in a situation where they only want to make one trip across the field, do it all in one shot. So be cognizant of that. And again, that's with consultations with your growers and clients and that, in which you have to take all that information into consideration. So basically, I'll kind of finish up here to summarize. Ensure that basic information about the soil sample is correct. That's on the report. Your field location and that's all correct. Client ID and that. Make sure that your soil sampling procedures meet your objectives and you do proper soil sampling techniques. Pay really good close attention to the units that are on the report. Every lab is different and they report different nutrients with different units. So pay attention to the units. The recommended nutrient rates provided on a soil test analysis are generally for the actual amount of nutrient, so the amount of N that's needed, not the amount of fertilizer. So for example, it'll give you a recommendation for putting down so much N. Well, we have different fertilizer forms of N. Urea, 4600. We have liquid N, 2800, and hydrous, 8200. So you need to work those calculations out so that you provide the actual amount of nutrient that's called for. So, and finally, on the soil test report, do the nutrient numbers that they're giving you make sense? If not, you may need to go back and resample that particular field to obtain more information or better information or confirm the information that's presented to you on that test. So with that, I will stop. I see it's just about 1 o'clock, so hopefully I've left time for a few questions. So Brittany, are you there? Brittany?
Hi there, sorry about that.
That's okay, Brittany. You can hear me?
I can hear you. Thank you so much for that great presentation. So we will now take questions. As a reminder, if you have a question, please type it into the question section on the right-hand side of the webinar screen, and I will directly ask you the question for you. While we're waiting for people to get their questions in, we have some that were sent in ahead of time, so I'll start with those. So the first one is there a best test method for measuring phosphorus levels in pH soils greater than 7.5?
The best one at the moment, probably that modified Kelowna would probably, if you've got a real high pH soil, that would be the best one. Melick and Bray, really for lower pH, kind of under that 6.1 or 2 pH level, that's for Melick and Bray. And I see soil test reports all the time where Melick and Bray is used, and that's because wherever that particular lab is located, they have more acidic or lower pH soils, and so that is a common test that they do. So, but if you've got a soil sample in which you've got a really high pH, that Melick and Bray does not really give you a good factual number. You need to look at that through the modified Kelowna or the Olsen bicarb method.
Okay. The next question we have is, can you address the relevance of certain nutrient ratios to soils in Western Canada, i.e. calcium, magnesium, and potassium?
Well, calcium, magnesium, because we've got pretty high pH soils. So we've got soils that are really quite dominant with calcium and magnesium. So really those are nutrients that really don't need to be added very much. It's kind of an uncommon, I shouldn't say uncommon, but it's not a usual nutrient that's applied here in great amounts, unlike our 4 big macros, NPKS. Did that answer the question there, Brittany?
Yeah, no, I think that makes sense. The next question I have is, how can this info inform backyard gardeners in urban areas? How can this inform consultants assisting at-home gardeners?
Because garden soils in urban areas, that is soil that was originally probably displaced and then has been brought back. So if you've got a backyard garden in Stonebridge or wherever, once upon a time, that topsoil was stripped off there when they developed the area, and then the topsoil is brought back. And it may not even be topsoil that was actually originally on that particular field to begin with. It may be topsoil from a different part of the city or a different field or that. So that is soil that comes back. It's disturbed soil. It's not original field soil. So again, that if you get a soil sample taken, you're going to be growing your vegetables and whatnot, kind of in that upper 0 to 6, 0 to 12. Get a sample, send it in to find out what your numbers are. You'd have to probably search online to see what recommended nutrient levels are for your vegetable crops and that. So something I'm not quite as familiar with in the garden soil. So.
Right. It's interesting though, like when you say that, yeah, of course that soil is brought in from elsewhere. So, you know, the nutrients in it might be different.
Absolutely. Yeah. And it's been disturbed. It sat in a pile. So there was probably, depending on where they took it in within the pile, that, you know, when the cats strip soil off of an area that they're going to develop, the soil gets piled up in a great big kind of a big hill in that. Depends on where that soil was sitting in that, the amount of mineralization and mobilization of that. Depends on what kind of soil it was to begin with. If it was more of a coarse textured soil than that, you could have more nutrients that leached out of that particular soil and that over time. So a lot of different things could have happened to that soil before it wound up back in your backyard in the garden.
Right. The next question I have is, what would lime requirements be in a soil, and are you able to comment on the cost and product availability?
I can't comment on the cost and product availability. Liming is a very uncommon practice here in Western Canada because our soils are very high pH, very calcareous, and lime, which is calcium carbonate, it's just something that you just don't really need. Liming is a more common practice in the United States, you know, Midwestern US and that, Colorado, Kansas, Nebraska, places like that, Eastern Canada, because they've got soils that are of a lower pH, and so they're trying to bring that pH level up to meet the demands of the crop that they're trying to grow in that. So, but liming is just it's a very uncommon practice here in Saskatchewan. I've never run across a client or a grower, excuse me, that actually does that, because you simply don't need to raise your pH any higher than what it is.
Okay. So we have a good chunk of questions coming in, Tom. So I've just been informed that we'll keep answering them until they're all done. So I think we'll just keep going here. The next question is, what test should I ask for if I want to measure organic matter and soil life?
If you want to measure soil organic matter, again, it's what they call it's put into a combustion furnace. So what they do is take the soil sample and they'll put that in. If you want, you can get what they call total carbon. Total carbon is the inorganic carbon plus the organic carbon that will give you your total carbon. You can get the total carbon measured. You can then get the organic carbon measured. Total carbon minus the organic carbon will give you your amount of inorganic carbon, which is your carbonates. What was the second part of the question? Oh, soil life. So yeah. I'm assuming by soil life, you're thinking of things like the microbial biomass. And that's probably a fumigation. They'll go in and they'll measure the amount of respiration that organic, the little microbes like bacteria and that will give off. That would probably be a much more expensive test for them to do, and that's one that's just simply not a common test that's done in a lab.
Okay. Another question we have is, you mentioned there are 2 ways to measure soil pH. Does it make a difference to the results if one method is used in place of the other?
Well, what the buffer pH does probably you should get and most labs will do the actual soil pH of the sample. The buffer pH, as I explained earlier, and I'll repeat, basically what they're doing is they're adding a chemical to your soil sample. They measure the pH first, okay? So they got a number. They then go in and they take part of that sample or a subsample, and they'll add a buffer chemical. They know what the pH of that buffer chemical is. They'll add that, and then what it does is it will raise the pH of the soil, or what the soil's buffering capacity is. What that is done for is for the liming requirement. So again, labs in the Midwestern US and that, where they do a lot of liming on fields and that to raise soil pH, they want to know how much lime do I need to put on a field? Do I need to put 2 tons on, 3 tons, 1.5 tons, whatever, to raise it? So they'll measure that buffering pH and that to get an idea of, okay, if I add this much, it can raise my pH from 5.7 to 6.4 or whatever. And then they'll be able to do a calculation and determine how much lime then they need to put on that field to get that pH in the soil in the field up to that desired level.
Okay. The next question is, there are pockets of soil in Northwest Sask that are quite acidic, as low as 5.5 at 3-inch depth. Are you aware of any nutrient deficiencies, either macro or micro, at that low pH that would have significant yield impact?
Yeah, soils that do have pockets where there's much lower acidity will have an impact on crop yield, and that will have a big effect on things like phosphorus. Because once phosphorus, you drop that pH level down into those types of numbers, that 5.5 or whatever, that's going to tie that phos back up again, and it's going to be dominated, and it'll be the iron and the aluminum ions, Al3 plus and that, Fe2 plus, that are dominating, and that will tie that phos up. Conversely, when you've got really high alkaline soils, really high pH soils, 7.5, 7.8, 8 and on, that the calcium magnesium dominates, and that will tie up the phosphorus. That's why that phos guy, he's a really kind of he's a different breed of cat compared to elements like nitrogen and sulfur. What the nutrient deficiencies are, I'm not aware of the actual numbers. No.
Okay. The next question: what about selenium? What is average for Sask soils, and how important is it for plants?
Selenium is, I didn't cover selenium. It's not that really of an important an element, really. I mean, more so your boron, copper, zinc, iron, and manganese are probably your 5 most important micronutrients. Selenium is not, and I'm not even sure what the, I'd have to look and see what the actual test is that they do in a lab, and I don't actually recall on any report ever seeing a mention of selenium. So that's the most I can comment on that.
Okay. The next one, so are any of the micronutrients not suitable for foliar application? Which are most important for early application?
Probably things like copper, which is generally, if it's soil applied, that's the best way for copper, and that's the old bluestone, copper sulfate. Again, generally in a field, you don't need to blanket the whole field with copper sulfate. Micronutrients are very expensive, and so I know that micronutrients are pushed more than the macronutrients because the profit margins on those are higher. So I understand that but most of the research, most microelements, probably, let me think, copper should probably be soil applied. Zinc, I know work has been done by Dr. Shino. The foliar applied was not as successful as the soil applied. Boron is probably soil applied, not a foliar applied. I don't think there's been any advantage whatsoever to applying boron in a foliar spray. Iron levels, Generally, Saskatchewan soils are not usually deficient in iron, so that one is really kind of a one that's really not doesn't really need to be too worried about. So that's.
All right, thank you. When fall floated fertilizers are applied, how reliable are spring soil tests?
Probably, if you're applying that in the fall, it's probably best to soil sample before that goes on in the fall. Spring soil sampling, it depends on the slope of the field, texture of that. You could have some of that gets washed down in the profile, and goes out of the sampling zone. Some of it could be washed, surface washed with snow melting. Things in this particular area of the country, snow melt is most of the time, our major moisture event of the year, because we don't usually get heavy rains like they do in Washington State or Pennsylvania or Ontario, and that. So some of that nutrient can then be washed down out of the or even off the field with overland flow, or moved downward in the profile with as the soil is thawing in that, and water movement that's leaching down in the profile can carry some of that nutrient down. So really and truly, if you're going to put that on in the fall, you should find out beforehand how much you actually need, and I would sample before you put that element on in the fall. So.
And then, so are you doing like a baseline sample in the fall and then following up with it after, or just one sample?
Probably just one sample, because I mean, sampling is an expense. It's an expensive proposition. So to sample in the fall and then again in the spring, most growers or producers are not going to want to spend money doing two samples on the same field within 6 months of one another. So it's going to be one or the other. And if you're going to apply nutrient in the fall, it's best to find out what's there in the fall after you've harvested, what's in the bank, i.e. your soil, and that what crop you're going to be growing next year, and that. So then you can base your recommendations that on what the future crop's going to be, what's in the bank, what now do you need to add if you're going to add something in the fall.
Okay. All right, so we just have 4 more questions. The next one is, how much error would you say is normal in soil testing? I've heard around 15% error.
Oh God, it would depend on who's sampling, the fields, the labs that those samples are going to. That's something I'd have to check with maybe Edgar Hammermeister or Jeff Shano about to see if that's correct or not. I'm not sure. I can't comment on whether that's a true number or not. If you're doing good, proper sampling techniques, you're sampling in the areas of the field that, you're not just sampling low spots, or you're not just sampling high spots. You're not on approaches or fence lines or in old yards, and that your samples should come back as fairly accurate. But if you're not doing proper sampling techniques, then as I mentioned earlier, GIGO, garbage in, garbage out, then you're going to have more erroneous information on a sample. So, but as 15%, I can't comment whether that's a true number or not.
Okay, thank you. What is the value of fall versus spring soil testing?
If I had to make a choice on my fields, I would always go with fall sampling. After the crop has come off, find out what's there in the bank, and then that gives me time, if I want to float some like potassium on or whatever in the fall, find out what I need to put on in that. I would go with fall sampling over spring sampling every time. However, that being said, sometimes, again, you've got this mystery number or these numbers that you think are, oh no, that can't be right for FOSS or whatever, and you've got to go back to a field and you've got to resample it again. Sometimes something that I've heard of, and certainly that's something we saw this fall, because we were sampling well into November with the late harvest and when you got into the end of October and started going through November, we had a lot of periods where we'd have some really bad cold. then it would warm back up again. Then we'd have some cold weather again. So we'd have a lot of freeze thaw going on. And you can get, and this is oftentimes seen with phosphorus, you can get some really high phosphorus numbers in a soil sample. And it could be that that is due to kind of the freeze thawing, kind of the release of nutrient from crop residues and that, and you're getting that in your soil sample. So, and sometimes, and in our company, we do have to go back and confirm that number or dispel that number, go back and sample again and grab a sample. But every time I would always go and do fall sampling. Most of the time you've got more time in the fall and that, whereas spring is a much more rushed event in that, and labs have a little bit more time to analyze the numbers in that, so they're not as rushed in that. So I would go with fall sampling every time.
Okay, this is our second to last question. How do you compare the Olsen results with the modified Kelowna?
Either or is good. They're both good on alkaline soils, and so either one could be. I know probably Olsen bicarb is probably the more common. Where I in our research lab, we usually use the modified Kelowna extraction because we actually did that because you can do that with not only the phosphorus, but you can do that with the potassium as well to measure potassium. So either or is good. If I had my choice, I'd probably say I want modified Kelowna, but if the lab doesn't do it, then Olsen bicarb. And again, our soils here are, most of them are high pH soils, so the Olsen bicarb one is to go through. If you've got, and again, we do have these, as you pointed out earlier in one question, some pockets where we've got lower pH soils, then that's where Bray or Melick will certainly, Olsen will still do a good job, but those ones are probably a little bit better one to use for lower pH soils.
Okay, and our last question. What are your thoughts on testing for AL and P SAT levels? I know labs don't test for them because they are usually only an issue in fairly acidic soils.
AL, aluminum, is that, could you repeat that again, Brittany?
Yeah, what are your thoughts on testing for aluminum and P SAT levels?
For aluminum, if you've got a low pH soil, the pH test is going to bear that out. And we know that the aluminum in lower pH soils, your aluminum and iron dominate, whereas in your higher pH soils, your calcium, magnesium dominate. So really, to test separately for aluminum, it's really not going to give you much more information than what your soil pH test is giving you in that. So again, if it's an extra, if the lab does it, fine. But I mean, it's really not going to really enhance things that much compared to what your soil pH number is going to tell you. So.
Okay, so that's it for our question period. At this time, I'd like to thank everyone for taking the time to join us for this webinar, and a special thanks to Tom for his excellent presentation. If you had entered your CCA number during registration, we will make sure to send those along to the appropriate person for you to receive credit. Credits are only available for those watching the webinar live. You can also easily find recordings of our previous webinars by visiting our website and searching for our webinars. For information on diseases mentioned during the webinar, they can be found at www.saskatchewan.ca/crops. If anybody has any questions regarding this topic or anything else related to farming, please contact your local Sask Ag Regional Office or the AKC, that's the Ag Knowledge Center, at 1-866-457-2377. And we will be sure to put you in contact with a specialist to help answer your questions. Thanks again and have a great afternoon.